Let us think about a type of discrete distribution known as the Poisson distribution. The Poisson distribution is often useful when one is interested in estimating the number of occurrence over a specified interval. There are two properties that one has to make sure that it's fulfilled for using Poisson distribution. The first one is that the probability of occurrence is same for any two intervals. And this will kind of allow us to move between different situations or different intervals because the probability of occurrence is same for any two intervals. And second, the probability of occurrence is independent, so one does not affect the other. The probability of occurrence of one does not affect the probability of occurrence of the other. And if these conditions are met, one can think about Poisson distribution, and one can use the PDF of Poisson distribution to answer the questions that we see as one of the application on your screen. So one can think about number of vehicles that are arriving at the toll booth, number of customers who walk in at the teller, number of customers that are served at a particular counter, number of patients arriving at a center, and a whole host of applications where there is occurrence of something happening in a given interval. Right. So let's think about 6 patients arrive at a center every hour. And we are interested to find out the probability that there are 4 patients who arrive in 30-minute interval. Now notice the interval is here, it is in hour, and here it is 30 minutes. But since we have this property, our life will be a little bit more easier. So here in this case, we have mu, which is 6 patients, 6 times something occurs. 6 patients arrive at the hospital or center for checkup or whatever it is every hour, right? And that means that it's 3 patients or 3 occurrence every 30 minutes. Why we are thinking of 30 minutes? Because that's our question. Our question is to figure out the probability of 4 occurrence, 4 patients arriving, and that is going to be given by mu to the power x e to the power minus mu divided by x factorial, right? So that is mu is 3, mu is 6 per hour, so 3 per 30 minutes, and it's 3 because 30 minutes because we are interested 4 patients arriving, 4 occurrence for 30-minute interval. So mu is 3, x is 4, that's what we're interested to find out, the number of occurrence. E is the number e, then you have mu again, which is 3, and then x factorial, which is 4 factorial, right? E is 2.718, and so when you work out the math, you get 0.1680. So that's 16.8% chance that you'll have 4 patients arriving at the center every 30 minutes. Next, let us think about another type of discrete distribution known as the hypergeometric distribution. Now, hypergeometric distribution is a multi-step experiment, but the key feature is the success probability varies across trials, across steps, and that makes trials not independent of each other. This is in contrast to binomial distribution, where it was a multi-step, it had 2 outcomes, but one outcome was independent of the other across trials. So the probability of success does not change across trials. But here, the probability of success varies across trials. So one trial is not independent of the other. And this is a very, very important feature, or probably the most important feature of hypergeometric distribution. The PDF apparently looks intimidating, but once you look at the application, once we walk through the application, things will literally fall in place much more easier than it looks like initially. So let's take an application. Let's consider a situation where an inspector is going to randomly select 3 bulbs, 3 fuses out of 12 in a box. And this box, which has 12 fuses, we know that 5 of them are defective. Of course, we don't know which 5, and that's the reason why we are inspecting for testing. And our interest is to figure out the probability that we'll find out at least one defective out of this 3 that is being taken from the box which contains 12 fuses and 5 of them are defective. So we are going to randomly pick up 3. Now keep in mind that we are not interested in probability of 1. Right? We are interested in the probability of at least 1. Right? So one can think about probability of 1, so that's at least 1, or probability of 2 plus the probability of 3, because we're going to pick up 3 fuses, and this will give us at least one defective. Now this is a long way of doing things. One can use the idea of probability to think about at least one defective is nothing but 1 minus the probability that you find none of them to be defective. So 1 minus none is at least 1, right? So we would like to find out f of 0, probability of 0. For using PDF, we would want to see what is n, the uppercase n in this case, the lowercase n, the r, we need 4 pieces of information, and x. We know x is 0. So x is 0. R is the number in the population which are labeled success. So here success is labeled as defective. And so there are 5 fuses which are labeled as success, which is defective, 5 defectives. The box contains a total of 12 fuses, the total elements in the population. And then the lowercase n is the number of trials. We are going to have 3 trials. We're going to pick up 3 fuses. Once you have this in place, rest is just plugging in all this piece of information and doing the computation. So again, what is r? R is 5. X is 0. Uppercase n is 12 minus r 5, and then lowercase n is 3. X is 0, and then divided by 12 and then 3. Okay. So I'm just using the PDF and all the information in the given application. So this will boil down to 5 factorial, right? Then 5 minus 0, 0 factorial and 5 minus 0 factorial. So that's 5 factorial again. That's 7 factorial. And then 3 factorial. And then 7 minus 3 factorial, which is 4 factorial. And then we have 12 factorial divided by 3 factorial. 12 minus 3 factorial is 9 factorial. Right? Now we're just doing the simple computation in your calculator. Of course, remember 0 factorial is nothing but 1. And so you use this whole thing is just 1. And when you do the math, you figure out it's 0.1591. Now keep in mind, this is not the answer. This is not the answer. The answer of probability of at least one defective is 1 minus probability of 0, and that's 1 minus 0.1591. Okay. And that will give you your answer to be 0.8409. So there's an 84% chance that at least one of them will be defective out of the 3 that has been picked up in a box which has 12 fuses and 5 of them are defective.